Online gameplay can be unique and unpredictable, and just a little more fun than playing a single-player game. But building for multiplayer has long been more difficult than its non-network counterpart. Keeping players in sync, mitigating latency, and maintaining secure gameplay. When developing for multiplayer, these are extra moving parts that we need to implement. Here's where Unity's network tools can help. In this video, we'll cover the basics of developing multiplayer games using Netcode for GameObjects. This guide will give you a solid foundation in multiplayer networking before you dive into our network samples. You can also download our free ebook to help you get started. Follow the link in the description to get your copy. If you haven't yet worked in Unity's Netcode frameworks, or if you just need a refresher, let's cover the basics and set up a simple network project. If you're just starting out with multiplayer, you'll likely begin with Netcode for GameObjects. This high-level framework adapts the familiar GameObject and MonoBehavior workflow for network multiplayer. If you're already an experienced multiplayer developer, consider Netcode for Entities, which uses the ECS architecture and data-oriented tech stack. This more advanced framework offers the highest performance and supports competitive multiplayer games with a massive number of concurrent players. Combine both of these frameworks with Unity Gaming Services, which offers a suite of tools to support your game's launch and ongoing player engagement. The basic idea of multiplayer games is that we're running the same application on multiple devices. These devices are arranged in a specific network topology, which structures how they communicate with one another. This demo will discuss the most common topology, client-server. Here, all the players run a client device that connects to a central server. These devices trade information over the network, enabling real-time gameplay. In this network architecture, clients handle user input and rendering. Each player has one client. The server manages game state and communication. It's the keeper of the game world and essentially the ground truth for everything that goes on in our application. Think of the server much like any other single-player game, except instead of inputs from individual controllers or keyboards, the server is receiving inputs remotely from its clients. At runtime, all the devices are exchanging information in the form of little packets of data, many times a second. This keeps them synchronized so they're working in unison, and that creates the illusion that everyone is playing together. Let's see how this works in practice with a simple example using Netcode for GameObjects. Create a new URP project. Unity 6 now includes the Multiplayer Center, which helps you with the setup of your multiplayer game. Navigate to Window, Multiplayer, Multiplayer Center. Select your game's genre and specify the number of players per session. The Multiplayer Center will suggest a Netcode solution based on those specifications. For this demo, choose Netcode for GameObjects and make sure to include multiplayer tools. Opt for the client-hosted model. Specify the packages to install. For the setup, we only need multiplayer play mode. Click on Install Packages to add them to your project. Confirm that in the Package Manager, you should have Netcode for GameObjects, Multiplayer Play Mode, and Multiplayer Tools. The Multiplayer Center simplifies selecting the right packages for your project. For this demo, we'll convert the Starter Assets third-person controller from the Asset Store to be compatible with Network Play. Import everything into the project and open the playground scene. Familiarize yourself with the controller as we'll be adding network capability. The player armature rig includes a character controller, an animator, and scripts to manage the animation and movement. These two components translate values from the input system to drive a custom third-person controller. In Netcode for GameObjects, a singleton network manager manages the network state. It sets up and handles the network sessions, connects the servers and clients, and spawns and despawns network objects. Add a network manager to the hierarchy by creating an empty object, then add the component from the Netcode menu. The network manager requires a network transport, a lower-level layer that handles communication. In the dropdown, select Unity Transport. This will add the Unity Transport component to the game object. Clients and servers communicate by exchanging data packets using protocols like UDP. By design, UDP favors speed over reliability. This is suitable for real-time applications, but UDP packets can be lost, split, reordered, or even damaged in transit. To address some of its limitations, Unity Transport enhances UDP with extra reliability and security features. Though you can use a custom implementation, in most cases, Unity Transport will cover your needs. Rather than focus on the lower network layer, Netcode for GameObjects lets us work at the application level. This allows us to build the game using higher level classes like Network Manager. When each client connects, the Network Manager instantiates a network object prefab to represent each player. All the players will use this common prefab, which you can set in the inspector. We can create the prefab using the existing player armature in the hierarchy. Make a new original prefab. Let's rename it so we know it's our network player object. Remove the original. The Network Manager will instantiate each prefab when a client connects. Then we can do a little bit of setup on the prefab itself, remove any unnecessary components. There aren't any physics in this demo. And to enable networking, add the mandatory network object component. Network objects can be spawned, despawned, and synchronized across clients. Having this component means the object can be shared across the network. Finally, drag and assign the network object prefab to the player prefab field. Before we actually start testing, we'll need to configure the build profiles. For the Network Manager to synchronize them, all network scenes must be available in the build. If a scene is missing, the Network Manager won't be able to tell the clients to load it. In Unity 6, you can create a custom build profile and add the scene, or simply add the open scene to the default platform. Then we can test multiplayer play mode. Our goal is to simulate the same application build on multiple devices. Previously, developing multiplayer games required making a new build every time you needed to test a change. With multiplayer play mode, you can simulate multiple players directly within the editor. To see it in action, select Multiplayer Play Mode from the window menu. This dialog lets you create up to 3 virtual players using the current project's assets. We'll just use one for this demo. Check the boxes on the left to enable a virtual player. Each one activates a client window. Enter play mode. Adjust the layout of each client to fit your desktop, showing the scene view, hierarchy, and inspector. Clear some screen space. You'll need to compare the windows side by side. Go back to the main editor window. This will simulate our host device. In the hierarchy, locate your Network Manager object under Don't Destroy Unload. In the inspector window, find the buttons at the bottom, then click Start Host. You'll see the player character appear. We'll leave the Cinemachine camera disabled for this demo. The important thing is that our character is active and can move around the level. In terms of network topology, a host is just a server that's also running one instance of a client. Even though our game only shows one player, it is in fact a network application running within the editor. Let's add another client so it actually appears like this is multiplayer. In the client window, locate the Network Manager, then choose Start Client. This connects the client to the session. Switch focus between the two windows and give it some keyboard input. The game works, but both clients control the same character, which isn't our intended behavior. Before we fix this, let's enable a helpful visualization tool. Since the player objects are identical and sometimes spawn on top of each other, it can be hard to tell them apart. The network scene visualization tool can make that easier. You can see that's already enabled in the lower left of the screen. This is part of the multiplayer tools package that we installed earlier. To enable it, select Window, Multiplayer Tools, open Network Scene Visualization from this dialog. This creates a small palette above the scene view. It has multiple tabs that display some useful real-time information. The first tab shows bandwidth usage. The bottom tab shows the settings. Switch to the Ownership tab in the middle. Make sure that text overlay and shading are enabled. Each prefab is now numbered and color-coded, showing ownership. The host owns instance 0 and the client owns instance 1. Our goal is to have the inputs from each client drive its corresponding prefab. We can create a client player move script to do that. At runtime, this will enable or disable components on the player prefab based on ownership. That will limit certain behaviors or input to specific player instances. Note that this script inherits from network behavior. This is a specialized mono behavior that includes extra lifecycle events and properties that help manage network objects. Inside the script, we still have access to the mono behavior methods like awake and update, but network behavior also comes with methods like OnNetworkSpan. That's invoked right after the client connects to the session. We'll use this instead of start. In awake, disable the two inputs and the custom third-person controller, then we'll override that in the OnNetworkSpan method. Here we check the IsOwner property to verify if the current client owns the player network object. If that's true, let's enable the necessary components. This ensures that only the owning client can control the player prefab. Add the client player move script to the prefab, then set up the fields to reference the components. Save and try multiplayer play mode again. Each player now controls the correct instance, and you can confirm that in the scene view. Note that the network behavior disables the update loop of certain components selectively. Our new runtime logic ensures that each client only controls its own player. However, the client's actions aren't reflected on the host and vice versa. Though we're controlling the correct player characters, the missing ingredient is synchronization. To understand how we'll make each player instance match across the clients, let's look at how the client and the server synchronize data using UDP packets. In a network game, the client will send updates about its network objects to the server. The server will then process those and broadcast the updated game state to all the clients. In this case, these states include transform and animation data, all carried by UDP packets. Visualizing this exchange on a timeline, the server updates the game state at a fixed interval known as the tick rate, while the client has its own update rate. A UDP packet takes a small amount of time to travel from the client to the server, and then the server sends a packet in response. This is the basic mechanism for synchronization. Higher rates and shorter round trip times mean smoother and more accurate gameplay, but require more processing power and bandwidth. Netcode for GameObjects includes built-in components for synchronization. Besides network behavior, there are specific components optimized for certain data. In this case, we'll use the network transform and network animator. Add these components to the player prefab from the Netcode menu. Network transform will sync position, rotation, and scale, while the network animator will manage animation states. Assign the animator component into the empty field. Disable any unnecessary axes in the network transform. For example, if you don't need to sync the scales or the X and Z rotations, you can uncheck them. This reduces the amount of data sent across the network, optimizing performance. After saving changes to the prefab and testing in multiplayer play mode, the host now works as expected with movements and animations synchronized across the client. This works from the host, but the same can't be said about the other direction. If you focus on the client window and try keyboard input, it's not working. The player remains at 000 because the client lacks authority to update the server. By default, many other network components like network transform and network animator use server authority. That means the server has the final say in updating and validating the state of network objects. In the case of our player rig, that means its position on the host is 000. Even when applying inputs from the client, the network transform overrides those inputs, syncing the coordinates 000 back to the client. Input works on the host because it's the same device as the server. It doesn't have the same sync and overwrite issue. To fix this issue, one strategy is to use owner or client authority. This allows each client to control its own network transform and network animator. This approach is simple to implement, but has some caveats, which we'll discuss in a little bit. Let's start by creating a script called client network transform. This will inherit from network transform and overrides the onIsServer authoritative method to return false. And that's all that it does. Next, we'll create another script called client network animator. This will inherit from network animator. And again, it simply overrides the onIsServer authoritative method and returns false. These components give each client control over its own transform and animations, respectively. Replace the existing network transform with the client network transform. Uncheck any unused axes. And likewise, replace the network animator with the client network animator, and then fill in the empty field with the animator component. And now in multiplayer play mode, each player controls its own network transform and network animator. When playing on the host, it syncs to the client just as before, but this time the client calculates its own transform and animator components, and the host shows the results correctly. And while this seemingly fixes our issue, like most things in software development, every decision we make is a trade off. One of the main issues with client or owner authority is cheating. When individual clients control their own state, it opens the game to hacks or mods. These could theoretically make players invincible or allow them to teleport or do any number of things that could disrupt gameplay. Exploits or hacks can ultimately doom a competitive game, so you have to be mindful of security when developing for multiplayer. The other problem with owner or client driven authority is consistency. In a competitive game, if player A dodges an attack, client authority shows this movement immediately. However, any kind of latency or network traffic can delay the data reaching the server. When the server updates another client, player B, the delayed data causes discrepancies. Player B might see player A in a different position, leading to unfair gameplay. A lack of definitive ground truth can impact a competitive game. As a result, client or owner authority is usually acceptable only in a casual co op or non competitive setting. In general, it's preferred that the server reconciles inconsistent states. To revert back to server authority, remove the custom client network transform and client network animator components. Then replace them with the default network transform and network animator. Remember that you can think of your server as essentially a single player game that's getting its input remotely. For clients other than the host, we'll send the input data across the network. In this demo, we'll use a remote procedure call, or RPC, to do that. An RPC allows a client to call a function on a server, or vice versa, across the network. An RPC is just a method in a network behavior that's modified with an RPC attribute. And here are a couple of examples. The RPC attribute needs a target as an argument. You can use send to server to make sure that it runs only on the server, or send to not server to send this to every client that's not the server. An RPC also requires a naming convention. The method name needs to end with the word RPC. Let's define this RPC in the client player move component. We want to enable the third person controller only on the server, so we'll move this logic into a block protected by the isServer property. Next, we'll define the RPC itself. We'll call this update input server RPC, give it an RPC attribute, and then pass in send to server to ensure that it runs only on the server. This method will take several inputs as parameters, and then just calls the corresponding methods of starter assets inputs. Though the network behavior exists on both devices, the RPC means that when you call this method on the client, this logic only runs on the server. And you can take a closer look at the starter assets inputs component to see how that works. These hold the input values, and that's what actually passes to the third person controller. The handy part is that we have these public methods to set them, and those work even if the mono behavior's enabled flag is set to false. Back in the client player move script, let's sync every frame in late update. If we're not the owner, just return early. Otherwise, we'll get the move, look, jump, and sprint values locally from the client. The client that owns the player will call the RPC using those local values. But this logic that drives the third-person controller only processes those values on the server. And just like that, we have some remote input being passed to the server via an RPC. On the server, the third-person controller gets those move, look, jump, and sprint inputs, but not from the keyboard. It's getting them from a remote method. Those inputs then drive the character on the server. Because the player armature has a network transform and network animator, the resulting motion syncs back to the client. And then that restores server authority with a minimum of extra code. And our result is a very basic application where the players can synchronize their movements and animations. Thanks for joining this introductory journey into Unity multiplayer. Though we've only scratched the surface of what's possible with Netcode, consider this a hello world for multiplayer networking. There's plenty more to wrap your head around, syncing game state with network variables, managing latency, applying client-side prediction. It's a whole new way to think about Unity. To further your learning, we have several Netcode demo projects that you'll want to explore next. The bite-sized samples are a great place to start. They offer small, discrete, and focused scenes showcasing specific network features. There's a simple space shooter where you learn about network physics and network object pooling, a client-driven sample where you interact with a 3D environment using a third-person controller, much like in this demo. A social hub sample showcases distributed authority in a 64-player sandbox environment. Dynamically reassign ownership across clients, and seamlessly migrate the host when the session owner disconnects. When you're ready, take a look at Boss Room. This is a long-running Netcode demo with several full-featured systems that showcase how to deploy Netcode tools in a production context. For advanced users with multiplayer experience, Megacity Metro shows how to connect a massive number of online players, complete with client-side prediction and lag compensation. To assist you as you continue your journey into Unity's Netcode solutions, we produced this ebook to help you get started. It provides a quick introduction to basic networking concepts, allowing you to explore Netcode for GameObjects or Netcode for entities on your own. Download the ebook today to begin building with one of Unity's Netcode solutions. It's a great time to be developing for multiplayer using Unity 6. Thanks for watching.